Start recording. Hello everyone and welcome to Handmade Hero, the show that we code a complete game live on stream. We are in the middle of some lighting stuff, and we kind of have a bit of a question, a conundrum to deal with today. Today is day 404, which of course means that this episode will not be findable by HTTP. But if you take a look at where we're at in the code base, I'll show you what we threw in at the end of the stream yesterday, and it kind of brought up a good question that we, I think, need to or want to address relatively soon. So here is the current little test room with no lighting in, and then if I go ahead and run our sort of offline test lighting version, you can see the reflector solution for it. And if we go ahead and switch to viewing the actual world colored with the lighting solution, you can actually see that, oddly enough, it's starting to look pretty nice in terms of how the lighting gets computed. However, we do have the sort of question I was asking at the end of the stream last time, which is, what are we going to do about actually reconstructing the per pixel lighting from the, coarse lighting computations that we do? And what you can see here is that in some circumstances, when because what we're actually sending down here is a vertex-based lighting, just as a test. And so what you can see here is we're computing the lighting at the vertices, basically, not exactly at the vertices, but a better way to say it might be we're putting little panels near the vertices to determine what we think they should be, we think they should be lit, and then each one of these cubes, or sprites as well, depending on the circumstance, is getting lit by interpolating amongst that solution to give it a color wash. And what you can see is that actually looks really nice, like here, or here, or here, and here, down in this area, and so on. It actually looks pretty good because you end up with a solution where the lighting tends to be fairly smooth across the vertices and doesn't vary very much. But the problem that you quickly get into with doing the scheme this way is when you do the interpolation, you can see how you get banding in cases where you've got two dark vertices and two light vertices opposing each other. And it just does not produce a satisfying lighting solution at all, right? It's definitely not something that you would want. You just don't want that look, right? That's not going to be satisfying at all. All of the lighting that we're contemplating doing is approximate, so it's not as if there's something inherent in here that I'm objecting to in terms of its accuracy. I'm just objecting to the fact that we will have these artifacts, and we don't want those artifacts. So what we're trying to do here is come up with some way of making it less likely that we'll get artifacts of this nature, and that way we can I just want something that will produce smoother, nicer results here. And the question that we have to address in order to figure out how, what our strategy is going to be for avoiding that problem is that we don't know how we're going to be reconstructing the lighting from a lighting solution. We know we are going to have a lighting solution that will be coarser than the optimal solution in terms of bouncing light around. And I'm actually starting to be relatively pleased with this sort of reflectors idea here and how it's working. Basically just light samples that are taken throughout the world. And we actually do relatively good lighting computation on those. I think we're going to be able to make that work, I suspect. I'm not sure, but I think we probably will be able to make it work on the GPU, and so it'll be able to run reasonably quickly. However, what I don't really know how we're going to do is take that, and no matter what we do, right, we're going to have something like this, like where it's a coarse sample of lighting. I don't know how we're going to take that and convert that into actual lighting for the pixels in the game. And there's a number of different ways that we could try to make this work. And I just don't know which of them is going to be the most intelligent, or I shouldn't even say that. It's more that I don't even really know what the space of total options are inside the space of what we could do. Like, I just don't even really know what all of our options are. If you look, you can kind of see that if you just take a look at these reflectors here, then, you know, one way we could approach this problem is by just trying to use these sample points for the lighting as something that we gather up to compute the lighting at any given pixel, right? And that's a pretty reasonable way to approach this problem. It's just an interpolation problem. So the idea is the first pass splats down a number of different light samples like this, and then the rendering actually per pixel just goes and tries to find what light samples are close by, right? Now, the problem with that, and I'm not sure exactly how we would want to deal with this, but there's a problem with that kind of a scheme, like the gather light kind of a scheme. And that is what happens at edges, such as this one. So if you take a look at you know, if I swap between these quickly, you can kind of see what the problem would begin to be. If I want to know what the color should be in this area, then, you know, I'm sampling the lighting from, say, this and this. I don't really know where it goes from red to gray, right? I just know that somewhere in between here it changed. And so we would have to kind of have a relatively smart reconstruction filter, probably something which said, oh, you know, this surface, the lighting samples from this surface and the lighting samples are from this surface. When I'm reconstructing this surface, weight the samples from this surface more heavily than from this surface or something. Because otherwise you end up getting a lot of way too much color bleed. Like this right here will be like fully red like this as it interpolates between the red and the gray. And that's not really what you want, right? You want a nice hard edge there like we have now. This is really the more accurate way to look at that. And so, you know, again, like I'm not 100% certain how we really want to do that. So it may be that we just want to send down local interpolators. One of the ideas that someone came up with on the last stream, or I mean, at least this is how I interpreted the idea. I don't know if this is exactly what they're going for, but one of the things we could do is per quad just send down the 4 interpolation points, have our own interpolation scheme that we use, and just go from there, right? Meaning we don't actually do a global gather at all. We just do an interpolation scheme that's not based on that. And if we think about how that would have to work, it's actually not that difficult to determine how that should probably work. Basically, all we need to do is come up with some different way of specifying the color wash over the surface so that it doesn't have that sort of banding artifact kind of thing happening to it, right? So that idea was the last thing we discussed, right? It was basically saying, well, oh, you know what? I forgot. We got to free up some GPU resources for Milton. So if you take a look at what's going on with the current interpolation, the current interpolation is doing interpolation like this. So let's say we have dark, dark, and light. And then we imagine it's a quad, so you know we get the problem where there's light over here as well. So what'll happen here is, because dark and dark are on the diagonal here, this entire diagonal will be dark, right? It will always be completely dark. In fact, if you imagine that these are just the value 1 and the value 0, and we have the value 1 here, What you can see will happen when you do this kind of interpolation is that everything across this line will be 0, because the linear interpolation across this line, right, will always stay at 0. There's never anywhere else for it to go, because this point isn't involved in the interpolation across this triangle line, right? So this point will correctly be 0.5. You know, that is what that point will be. But this point will still be 0. So that's why you get that dark band that comes down. So the other question is, well, what would happen if we were doing proper bilinear here? You know, what would that look like? So if you imagine we had bilinear that was, you know, built on the same distribution of magnitudes, then along this diagonal we no longer get that same behavior, because if we bilinear these, no matter which way we do it, we're going to get 0.5 here, and we're going to get 0.5 here, right? Because we know that's true. We know that even if we did it the other way, we would get 0.5 in both cases, right? And so now, when we interpolate this position, we're actually going to get 0.5 here, right? So this produces a more rectilinear blend of the colors, which because all of our stuff is rectilinear, may well produce less objectionable artifacts for this very reason. So what this would do instead is this would produce something that was like bright up here, right? And then got sort of a little bit darker as it got to here, right? The standard bilinear interpolation pattern. And then as we got further out to the 1, right, it's going to have the same thing here where it's got kind of a bright bit here and then darker like so. And this is that part is very dark there. And so you could imagine this producing a less objectionable artifact, perhaps. However, you're still going to end up, I think, if you went this route, and we could test it certainly, but I think, you're still going to end up with objectionable artifacts. They're just going to be crosswise, right? You're going to end up with weird like patterns that look like this sort of a thing. Just like you do with bilinear filtering, right? You know the pattern I'm talking about. It looks like this kind of a thing. I don't know if we can find someone who's drawn that diagram. Bilinear. Yeah, it's right. In fact, there it is. Very first thing. So do you see those plus patterns? Those plus patterns is what we would get kind of blown up pretty large, right? I don't know if there's any other images that would show it. Well, doesn't look like it. Looks like these are all talking about sort of something a little more, not really. Well, there you go. That's a pretty good one too. Right? So this right here is not sure what exactly. This is a curve-based one or whatever. Yeah. This right here is the kind of thing that we would see sort of in the centers of our pixels, I think, and potentially around edges. It's, again, like I said, kind of hard to really know exactly what it would look like. I don't know if I can zoom in on this, can I? Yeah, there we go. So I can't tell. They don't have any of the worst case in here, like I was talking about, where there's 2 bright pixels on either side and 2 dark pixels on either side, which is kind of the thing that we want to see, but I need like a little thing where I can just put in something to bilinear filter. So anyway, the point there is simply that there's still going to be artifacts if we use a bilinear filter. However, this is lighting, and lighting tends to be more radial, right? Because the fall-off curve across a plane tends to be more about distance, and distance tends to be radial. It doesn't tend to be linear, right? It's linear along, a line, I guess you could say. You could approximate linearly, but not as that line becomes a plane, right? Because if you imagine, the light being very far away, and casting on here, then as it gets dimmer, it does form sort of a linear interpolation. But if you imagine the light being very close, then it's typically going to be very curved, right? So one thing we could think about in addition is saying, well, if we're going to interpolate lighting across a quad, and we've only computed things at the vertices, or maybe we even get a little fancier and compute more than just the vertices, like maybe we go nuts and there's just like tons of points that we computed. I don't know, right? But let's suppose we do something where we've got some number of sample points. We could choose to reconstruct them with something that isn't linear, right? We could use something like a radial, some kind of radial normalized interpolation, like a weighted sum kind of a thing that normalizes the contribution up based on a distance value so that these points are actually radial, right, and have radial interference patterns. And that, again, might give us something that looks more lighting-esque than reconstructing it with simply a linear interpolation. Since we probably have plenty of per pixel time to do that, I would think, on a higher end card. And we can, if we want to, play it a little bit fast and loose there and maybe do different things depending on whether we're on the front depth peel or not, right? Like our first depth peel. We could do stuff like doing the lighting differently per depth peel if we need to, speed-wise, or I don't know. That could lead to artifacts, so I'm not sure. On high-end GPUs, I really don't think we're going to have a problem because, they have so much horsepower to spare. And, hey, you can always turn lighting down to a low-quality setting if it turned out to be something we needed to get rid of. So point being, I think we would have time to do something fancier there, where the quads themselves are sort of shaded with something a little bit more fancy. And so if we thought about, if we took a look at how we were going to do that potentially, the problem is we need access to these things, in our shaders, right? And in order to have access to these in our shaders, we have to kind of, again, decide how we want to interpolate our lighting and how we're going to access the interpolation to our lighting. And so, again, that brings us just back to the very basic question of, do we want to interpolate across primitives or not, right? Meaning, is this going to be a global lookup of the lighting, or is it just going to be local to the primitive we happen to be sending down? Meaning, if these are our sample points, do we want to have all of these sample points available to the primitives so that when the primitive is shading itself, it looks up into, say, a texture that has these sample points encoded? Or are we going to do something that is, unrelated to this in some way? And you're just going to send down information for how to shade a particular triangle, right? Or something like this. And I really, like I said, I really don't know. So this is all experimental. I have no particular idea about what the best way to do this would be. What I will say is I'm definitely tempted to do something that uses all the samples, meaning that allows the per pixel reconstruction to actually take into account everything that it sees. Everything that we've computed. The reason for that is it feels a lot like throwing information away. If, for example, when we go to shade, this thing right here, we've really done ourselves a disservice, it seems, if we throw away the lighting information for the piece of the ground that's right next to it, because, man, that seems like useful information, right? And it seems like we could get much nicer lighting solutions by, gathering from the things that are close by. So it definitely seems like the kind of thing that's a little bit tough to... it's just the kind of thing that seems a little bit hard to pass up. It's like, it seems like we want to push that information down to the card. and have it do the reconstruction. So that raises the question of how we would store and how we would index, into something that looked like this. And again, that's kind of one of those things that I wish I had a better idea of how we should do it. I don't, but let me just talk through a little bit of it here. Oops. Of course, the classic cannot access the tablet. I do not know why that happens. No one seems to know. All right. So here we are on day 404. Lighting lookups. So what I need to do here is I need to take what is essentially spatial data, right? So I've got, let me take that corner case that we have there, for example. So let's suppose we're looking at the place like this, where we sort of have the wall here and the ground here. And we're trying to light this stuff. So we know right now that we took lighting samples at effectively these locations, but that's not really the important part. The important part is we took some lighting samples. And those lighting samples we could really distribute anywhere, honestly, right? Because the point of the reconstruction is to take lighting samples that we distributed and do something sensible with them. So we probably don't really need to think too hard about where the lighting samples are. We just need to think about the fact that we have some lighting samples in space, and now we need to reconstruct lighting from them, right? Okay. So once we have these lighting samples in space, then what we want to do is say, okay, when I am computing something like one of these pixels, I want to be able to take a neighborhood around where I am and see what all of the lighting is in that area, right? So it's kind of like a spherical query. Wow, that's some handwriting. There you go. So it's kind of like a spherical query in a sense that what we would ideally like to do is we'd like to be able to say, okay, I'm going to shade this pixel. Please tell me all of the lighting samples that are within, R, some radius, of me. And I'm going to take all those samples and average them together based on how far away I am from them, let's say. Right? By the way, this is some good lemonade. Anyway, so we need two things for this. First of all, we need to send samples to the card. Right? And we don't know in the future, those lighting samples might not be sent to the card. They may actually just be created on the card, right? So saying sending lighting samples to the card is really just for our current test purposes. So that's, this is really just something we need to do for right now because we would like to be able to compute lighting on the CPU at least for now. We may not compute lighting on the CPU in the long run. We may just have the GPU do it, but, that's neither here nor there. So at some point we have to send lighting samples to the card, which means we need a storage format for them. And number two, we need to be able to quickly spatially query them. Right? So we need two things. We need a storage format that will store these lighting samples in something that the graphics card can access. And the second thing we need is a way to quickly spatially query what lighting samples are near to a particular 3D point in space, right? Those are the two things we need. And in order to do those two things, the first one's pretty straightforward, I think, right? If we think about how we would store these, well, we know that a lighting sample is like an X, Y, and a Z, right? And then, you know, a RG and a B intensity. So really, we can just store this with two RGB textures. Maybe there's something more clever we would want to do at some point, but really, you know, without thinking too hard about it, two RGB textures will store them all. There's really nothing more to it than that, right? Then for the spatial query aspect of it, that part's a little bit trickier, but we do have options for it. So the simplest option probably is just going to be a voxel, right? So what we would do if we wanted to store a spatial query that was not particularly intelligent in any real fancy way, but which we, you know, like I said, wanted to construct something that was a relatively simple spatial query, we could do something that was sort of a, you know, a lookup structure that was, you know, 256 by 256 by, say, 32, something like this, which is not a huge amount of space, even though it is a voxel, right? It's, let's say we probably need 60, I guess it depends on how many reflectors we have, blah, 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 blah. So, you know, it's probably, let's say each one of those needs to be 16-bit. So it's 4 megabytes, which is not the end of the world, right? But in that 256 by 256 by 32 texture, what we would do is at each cell, we would just store an index to the texture set, right? So in this texture series here, in this these two textures, right? We've got two textures. Imagine that they were just either 1D textures or 2D textures that we treated as 1D textures. Either way, it doesn't really matter. But imagine that we've got, you know, the XYZ texture and the RGB texture. They're just some big list of lighting samples, however many we decide to take, right? And you imagine the first texel is 0, and then the, you know, 65536, well, 65535 is the maximum one. What you can imagine is in this texture, we just store a single 16-bit value that says where the textures for this, where the lighting samples for that block start, right? And we could choose to store a count in here as well. If we want to make this a 32-bit texture, so it's 8 megabytes, we could store an offset and a count. And then we would know how many of them to read as well. Or we could just assume that there is like a fixed number of, there's a fixed number stored or a null terminator, right? You could imagine that when the XYZ value that you encounter has some special value. So for example, if you just put, you know, inf inside X or something like this, you know you've hit the null terminator. So, you know, you've got different ways you can deal with it, and it depends whether you care about this texture getting bloated or this texture getting bloated. I'm not sure I know off the bat which one of those would be better. This RGB right here, this texture can be 24-bit. This texture here probably can't be. This texture here probably has to be actually a float texture or a 16-bit per channel texture, just because it's storing positions in space. And we need to be able to reconstruct that with some fidelity. So it suggests to me that this would probably be a fairly large texture. If we assume that this texture is, if we assume that this texture is actually a floating point, then it's actually 32, 64, 96 bit, because it's, right? So this entire thing, when taken together, is 96 plus 24 bits, or 120 bit, right? So yeah, if you think about an 120 bit texture versus this one, wasting space, wasting 120 bits in here every time you have an alternator, it depends. It's really hard for me to say. I really don't know, because in here this would bloat all of these, even the ones that don't have anything in them. So you know, if you made this one go from 16-bit to 32-bit, you're doubling the size of this. You're not doubling the size of this. So the fact that this one stores a lot more bits per, I don't know. You can see why it's a tough trade-off there. You'd have to kind of think it through a little bit better. But hopefully this makes some sense. The thing that makes me a little nervous about this in general is that it is kind of it's kind of compute shadery. I assume, let me see here. Where is the there it is. I assume, if I'm not mistaken, although I might be mistaken, I don't know if you can do, like, I don't really know if you can do anything sensible for creating this kind of a lookup structure on the graphics card, however. On the CPU, it's not so onerous because we're just doing testing, so we could pretty trivially create one of these on the CPU, obviously. But this wouldn't be a very good way to store it for GPU generation. And the reason for that is because packed storage of this kind is difficult for the GPU to recreate in parallel, right? Using atomics, you could make a linked list version of this. So you could add the lighting samples to the voxel as sort of using atomics. Every time you went to write one in, you would write one in and put a linked, like a next pointer effectively into one of them. So you could do something like that, but again, it's just pretty dicey, right? It's a pretty nasty operation to have to do. So we could do something like that, but it is going to be a little bit tricky. I don't know if we would therefore have to move up a level of OpenGL shading, because I don't know where atomics come in. I don't know when you can get atomic operations in shaders. They are a very old concept, but they're not... I don't know how widely supported they are, right? Let me see. So it seems like atomic counter is not really what I'm looking for. Let's also see here. Because I'm pretty sure that basically if we wanted to compute lighting on the graphics card and provide it to the game in a way that was easy for it to look up, I'm pretty sure that it would require fancier shading than what we have. I'm not 100% certain, but I believe it would be. I can't think of a lot of ways to look up lighting that wouldn't require that. But I could be wrong about that. I'm trying to think. Yeah, I mean, all I can say is if we want to do something now which will allow us to play around with it, this would be fine. Because creating this on the GPU, on the CPU is not hard. And we don't care how long it takes to run because we're just doing a test pass. So the problem is just if we wanted to do something, if we were trying to do something that was forward-looking, but I don't know how necessary that is because we don't really even know how well this will work, right? And it might be just premature to be thinking about how we will run things on the GPU before we've actually gotten to the point where we're happy with the results. That said, it is sort of true that we may not need something that complicated. For example, in terms of like if we did have a voxel where we eventually dump things into the voxel, maybe it would be possible to just use that directly to store the lighting information, where we just kind of average our lighting samples into a voxel after we compute them. I don't really know. And so you could just imagine getting your lighting from the voxel and just don't bother with the secondary lookup. I mean, if you think about it, right, you could imagine taking the lighting samples and rendering the lighting samples into a voxel as sort of just a rasterized version of the lighting, and then everyone reconstructs by just looking up into the voxel and interpolating between the various points in the voxel. And we could use a better interpolator than bilinear, or trilinear in this case. We could use a better interpolator than trilinear if we wanted to. It seems like not a terrible idea. It's not necessarily a good idea. But that would mean we wouldn't really have to deal with any kind of a like more elaborate lookup structure. Yeah, hard to say. Let's maybe try that. I mean, I guess we could sort of look at both options to a certain extent, but maybe we could just try that. And because if we wanted to, we could imagine that just sending down a very high resolution voxel is sort of an approximation to this anyway. So we could kind of also see by changing sort of the resolution of the voxel, we could maybe figure out to some extent how we wanted the how the lighting would improve if we were doing a scheme that more that used sparse storage in order to make things clearer. But yeah, but it does seem all right. All right. Okay. I could maybe believe that. So let me take a look and see what our options are in GLSL 3 here, in terms of sampling from a 3D texture. I assume we can do that because that's pretty old school, right? So you can see here we've got texture lookup for a 3D sampler, and we can just pass in a 3D UVW, and it will give us back exactly what we would have expected. So that seems pretty easy. No big deal there, I guess. Projective texture lookup with offset. We shouldn't really need anything else, I don't think. So it depends on the circumstance. We may want to do a texel fetch instead. This will give us back. Well, no, that might not be true. So if we turn off any filtering, then the texture lookup would give us what we need, I think. So I think we could just use the regular texture fetch with no filtering. And then if we want to, we can grab, multiple samples from the texture and average them together, or rather radially blend them together based on distance or something like I was talking about before, to give ourselves interpolation of the lighting. So the thing that makes me a little nervous about this is that I'm worried about the artifacts that we'll get from things moving across cell boundaries. So for example, imagine that you have a lighting sample that's right here and another lighting sample that's right here. When they get voxelized, they'll each be setting what the lighting is in their part of the voxel. However, if you then moved, if whatever this was a moving thing, and it moved so that on the next frame they're both inside one. I didn't draw this very well. Let me draw it a little bit bigger. So here's frame 0. Here's frame 1. And imagine that I have, two lighting samples, one here and one here. And then on the next frame, they're moving in this direction, so they both end up in the same cell. So if we do a voxel scheme that can't record all the reflectors, so they're not moving continuously around the world, they would have to get averaged together here, which means you'll get a very different lighting result on frame 1 as from frame 0, because in frame 0 you're considering the contribution of each one of those reflectors separately, and on frame 1 you're having to smush them together and they have to be considered as a pair, as a combined pair. And I don't love that, because again that puts us back to a sort of artifact, a pretty heavy artifact potential, I would think. So I guess I don't know that I really believe that putting things into the voxel as, just a single sample per voxel and everything has to get smushed down to that's really going to be what I want in the end. I suspect that I probably will need something that's going to treat each reflector individually and store all the reflectors. Well, I guess what I'm going to say then is, let's just do the original thing I was talking about, and let's see how it results, right? In other words, let's suppose that we're going to do lighting here, and I want to encode this lighting information into some bitmaps that a graphics card could accept and use to reconstruct lighting. You know, somehow. So if we imagined that we were going to do that, and I was going to do an output lighting here, and what I want to do inside this output lighting is I want to do like an output lighting textures, something like this. So what I want to do is I want to basically do a voxel where I place each reflector into into a voxel, and then sort of make those take that voxel and convert it into one of the texture formats that we that we can send to the card. So, for example, what I would want to do here is say that lighting solution as a thing notes intersummit, there it is. So if we imagine that lighting solution has some voxel information in it that it's going to generate, and also has some place to store these elements. Let's say I've got something like this. So I've got a position texture that's just going to be, you know, however many lighting elements I have at maximum, which is 4096 in this case. I've got a RGB texture, so that's just going to be, well, I guess there's not really a good way to do that, but this is the color texture, and it's going to be 3 of these each. And I don't think we really need, like, I could do a U32, packed U32, but there's really no point because we only need the RG and the B. I'm not sure there's anything else that you need there. So those are lighting samples. And then we need the Voxel Lookup. So the Voxel Lookup is going to have a count and a like a count and an index, essentially. And I guess that really, the count has to be small. So really you could probably fit the count and the index into 24 bits. You don't need 32 bits for that, because the count is, in fact, the count could even be, if you just used a single 16-bit value, the count could even be sort of snuggled in there probably with it, because you probably can't have that many in there. But we won't get that fancy just yet because that's probably putting the cart before the horse. So I guess we'll just say that this is the Voxel Lookup or something. And who knows what that is? I certainly don't, but probably something like that, right? So these are the things that we would send down to the graphics card. And like I said, I don't know if we want to just make this a 32-bit texture because, I don't know, there's nothing, the problem is there's nothing else for us to store in there, at least not that I can think of, because our lighting is just going to be RGB intensity, and there's really nothing else to put informationally in there. But I guess, you know, one thing we could say is we're trying to do this as a test, so let's just keep it simple since we have functions that pack this stuff already, and maybe that's just an easier way to go. So you imagine we've got our Voxel Lookup in here, and I guess, again, we'll make that a U32 because we'll use a 16-bit index and a 16-bit offset. A 16-bit index and a 16-bit count. for now. So there we go. Let's see how big that is. I'm just curious how much data that is. It's a lot. Oops. 4096 times, I guess that's 3 floats times 4, so that is 49. Oops. That's just 4,096 times 4. And I think we said this was 8 megabytes, right? Yep. So this is 16K. I guess we could just say 8M. And I guess 49, 152, oops. 1024 is just 48, right? So, you know, these are tiny, and that is understandable, right? Because those really don't take up any space by comparison, because there's only so many reflectors that we actually have, and they're not multidimensional, so they're pretty tiny. The Voxel Lookup is what takes up all the space, and of course that's because it's massively redundant, like there's way more space taken up by it than it probably needs. So, this is really good lemonade. You know, it's Newman's Own lemonade. I'm kind of a Newman's Own fan. I don't get paid to say that. I just am. They have really good little Numinos, the little like Oreo kind of cookie things. Those are really good. And so are the chocolate chip cookies. All right, so what we want to do is fill this out. And in order to keep this relatively condensed for now, like I said, to make it easier on us, we probably don't want to make it be a skip list kind of a thing. A skip list is probably the wrong word. A linked list. I don't know how we would create a structure like this on the GPU efficiently. And the reason for that is because things have to get packed. So the way we would have to do this, and we can do this on the CPU very easily, but on the GPU I don't know, or even just how we would do a fast version of it on the CPU also seems a little bit tricky. Which is to say that if we want to make it so that the all of the reflectors that occur inside a given voxel, that all of them are packed together in the PC texture list so that we can have just a count that tells you how many there are, and you read it, that is pretty difficult to do because that requires sort of pre-processing the data so that you know ahead of time how many go into each bucket and then fill the bucket. So in theory, we could test as well a more like a more likely version of this, if you will. And that would be something that was, you know, let's say like this. That would be something where we store, you know, that. So in here we actually have something like this. And each one of these stores the position of the light reflector and the next one that you should look at inside this array. So you kind of like skip through it as a lookup. That's something that's more likely to possibly be created on the card. Again, I don't really want to say that too firmly, but basically, you know, that it's more or less what happens. And then this voxel lookup would just be a single 16-bit. So just tell you where the first one was, and then this would tell you where the next one was. Now, of course, again, we don't really need a full 32-bit value here. You know, this could be a 16-bit value. But I'm not really sure I see a lot of ways of how we would pack the rest of this stuff down in a way that made sense. We still need 24 bits for the color, at least, and so that doesn't really help us. If we could make this an 8-bit value, that would be amazing, because then you could do this. And that would be kind of awesome. But unfortunately, if the element list is 4096 long, then having a next pointer that's only 8 bits doesn't really help you. And so it seems like that's a bit of a non-starter. So again, I think that's probably putting the cart before the horse in trying to make that work. So we're just going to leave it like that for now. We'll try to figure out how to do some shenanigans later to make that less problematic, perhaps. On the other hand, it is worth noting, like I said, this is the small part of the problem. So it's really not the most important part. It's the voxel lookup that's the big one, and that's kind of nasty, right? So let's go ahead and see how we would make something like this. I think you'll be surprised at just how simple it actually is, especially if we do a linked list version like this. Creating it is actually really basic. So if we have a lighting solution and we're trying to make one of these texture things out of it, we can actually do that pretty directly. One thing I can do is pull this out so it's a little bit more explicit. Lighting textures. And we can just call this P, C, and lookup. So if you, and I guess this is actually, this is like P next, I guess. It's both of those. So if you take a look at what happens here, we've got some number of lighting elements that we've computed, right? And when we do output lighting textures, we don't need to output quads, right? That's not necessary. So what we're going to do here is pretend that we're taking a lighting solution and we are going to take one of these lighting textures, and those lighting textures will get filled out by this routine. So the first thing that we want to do is we want to clear, right, everything in the lookup. Because we need to start with that lookup structure, the voxel lookup structure. We need to start with that being completely clean. So it needs to have 0 everywhere. And we'll just say that 0 is the sort of the null value. It's unused, right? And if we wanted to, we could also beef up this number if we want to be able to store more of these things. We probably should, but we'll get to that a little bit later. So when we come through here, when we start with a completely empty lookup, what we know is that every time we get one of these element values here, so let's take a look, for example, at just a single element value. So if you take a look at one of these element values, what we can see is we've got a front emit that we generate this way and can pack down. Excuse me. So we can create a color from it by doing exactly what we were doing before, where we pack this down. And we don't have anything to merge it with anymore, right? We're just packing in the front emit color of this lighting sample. Now, it's worth noting that we want to do something smarter here than what we have been doing. So what that front emit lighting is telling us is how much light we've received. I can't remember if we've modulated it by our bounce. I think we have. So what we're going to want to do is take that out of the equation. In fact, we can do that right now. Let's just do that. So what you can see, for example, in output lighting quads, what you can see here is we take the front emit and we just pack that down directly, right? When we're just showing reflectors. So what I want you to see here is when we run the lighting solution, sorry I'm coming at this a roundabout way, I'm not sure how to explain it other than to show it to you. What we see here is, I'm also not sure why that's running slower all of a sudden. Is it just because of the size of the thing changed? No, we don't need to upload anything. I guess it's just because we used more memory there? I'm not sure why that is. I feel like that's taking more time. I'm sorry, give me 1 second. I just want to know why that would be the case. Is world mode... No one uses the lighting textures. What did I do wrong? Maybe I'm mistaken. Maybe it was always going that slowly. Well, I guess there's not a whole lot we can do about it at the moment because it looks like it's entirely spent in swap buffers. Well, I'm not sure what to make of that. I guess we can investigate later. Anyway, so if we take a look at what happens here, back to what I was saying before. What you can see is, for example, this is red, and this is blue. That's actually not the lighting that's falling on this point. That's the lighting modulated by the color of the surface. And we actually want to stop doing that now. The reason we want to stop doing that now is because we're going to assume that a surface will take its color into account when it gets rendered. So presumably, because that way we can interpolate between lighting samples even if the two surfaces are different. So what we want to do here is we want to change it so that the way we were computing the front emit C, which is actually here. The way we're computing the front emit C, we want to here we go. When we do our light color and we do our bounces here, what we want to do is make it so that when we do this Hadamard reflect color, when we're computing our total light, so this is the total light that comes in, we actually don't want to do this here, right? What we want to do is just use the total light value as the result instead of as how much light we're storing as coming from this surface, like so. So, like that. And then what we want to do is say, okay, we still do want that reflected color to actually be what happens when light bounces off a surface. So when we are actually grabbing the light in the first place, right? When we say the source's front emit C, that is where we're going to do that multiplication. So the light color that comes in is going to be the source's reflected color times the source's front emit color, right? And so what that means is that when we store this in the first place, and we do that sort of front emit C color RGB part of it, right, where the color RGB is putting the ref C in there, we don't actually want to do that anymore. So we just want to set the front emission to be, you know, a colorless version, because it will get the color when it actually does that initial out, right? Okay. So now when we make this go, in theory, those should just be, well, all right, that did not go anywhere close to what I thought it would do, but that's okay. Somehow I took that out and it still did exactly the same thing. How is that even possible? Let's try that one more time. So, obviously, yeah, didn't do a very good job with that. I'm assuming it doesn't get modulated here, right? Like, it definitely doesn't. It's just the front emit XYZ, right? Yeah. Oh, awesome. I said I was going to get rid of it, and I didn't get rid of it. There we go. There we go. So now this is just a pure lighting solution that we're drawing, right? So it's the light that got bounced around and how it got bounced around. So if that makes sense. Now, what that means is you can still get red twinges and stuff like that when you bounce something off of like a red surface or whatever. And we should, in theory, be able to create some circumstances where we get very clear examples of that. And I will try to do that here. Let's see if we can. Get something like that. I don't know. I don't seem to be really getting it, so I may have messed something up. We'll have to check. Because there should be ways for me to get like blue bounce and stuff like that onto surfaces here, but I'm not really seeing it. So I think we still maybe have some problems here. Let me just double check what light color gets used for. Yeah. So in theory, this line should still take whatever the emitted color is going to be and color it by whatever the source's reflectance is, right? So we still should be getting that contribution. We don't really seem to be, which is a little odd. Why is photons received still here? There we go. So I'm a little weirded out by that because in theory, that bounce light should still colorize itself, right? Any light that bounces off a surface and goes to another surface should be getting colorized by this Hadamard product here, where the reflection color and the front emit color merge together to produce the light color that will actually get used for the diffuse contribution, right? So I don't really know why that's busted. Because it certainly seems like that should work. What is the global lighting render iteration count these days? 4, apparently. Since we're not using this occlusion iteration anymore, I suppose this is probably not super relevant. We could just get rid of it. Yeah, I don't know why I'm not seeing anything other. It's almost. I mean, there are some places where you do get a little bit of that bounce color in there, but it just doesn't seem nearly as much as I would have expected. Like, you get a very little bit there, but it's so little, it's odd to me. And I think that could be, I mean, it could just be because our lighting equations aren't real yet. Like, it could be that we just need to make our lighting equations actually be reasonable. But anyway, let's ignore that for now. I don't love it, but let's ignore that for now. And when we go through the lighting equations and try to make the transfer be more accurate, we'll pay closer attention to that. For now, I just wanted to point out the fact that this is now a more pure lighting solution that doesn't, that at every point tells you what the actual lighting is, not the lighting times whatever the surface is at that location. And so then if we go in here and say we don't want to look at the reflectors anymore, then what you can see is now we've got a solution that's a little bit more true because it gets modulated at the end by the vertex color. And so we were kind of doubly modulating before, which is not right. So this is a little bit more accurate, and this is what we actually want to send down, like I said, to the card in the first place for reconstruction. Okay. So now if we want to actually do this lighting pack, like I was saying, packing these things into a lookup texture, it's not very difficult. Like you can see, we do the simple pack here. We've got the color, and we know that now we just have to figure out a way to place these things into these lighting textures here. So we've got two things we need to do. First, we need to store the element's position and color into the lighting textile information, and then we need to add to the lookup chain this textile. So both of these are pretty easy to do, right? First of all, the only real thing is mapping the position correctly into the lookup. That's about it, right? So I guess there's two things we probably need to be aware of here. And mostly the only difficult part of it is the lookup structure. We have to figure out how that's mapped. But let's assume temporarily that we know where we are in the lookup structure. So let's assume we have something like this. So we have some way of knowing where this element is in the lookup structure, right? Let's say we've got that so far. Well, if we have that, then everything else becomes fairly straightforward. We know that wherever we're going to pack this this particular lighting element, we know what that is because every time we add a new element, we just increment by 1, right? So we basically have a pack index that starts at 0. What we're going to do is we're going to assert that the pack index is less than the number that can fit in here. And we're going to pre-increment it. Now, why are we going to pre-increment it? We're going to pre-increment it because I've said that 0 is not a valid value. So if I started at 0, I'm just going to pre-increment it and then do my test because I'm going to put it in this particular location, right? So once I've got that, I know that I'm going to look at my pnext at that location. And in fact, I could just call this pnext. And I know I need to set two things. I need to set the next pointer, basically, and the p-value. The p-value we just have, it's whatever the element's location was, right? And the p-next value here, we know that that's going to be whatever was in the lookup, right? So whatever was previously the value in the lookup table at that point, that's going to be our next pointer. Then we just do the standard linked list addition. We put ourselves at the head of the lookup. So that makes that voxel structure, we take whatever the chain was that was hanging off that point in the voxel, we make that hang off of us, and then we make ourselves the head, right? Very straightforward process. You've seen me do that a million times on Handmade Hero. So after that, we still need to use that pack index one more time because we also need to take our dest color here and store that. But of course, we can do that with just one simple storage. Right, there we go. And that's it, right? So really the only problem that we have is how to do this part. How to map into where the text is supposed to be. Oops. I don't know why there's a Hadamard still in there. I don't need to multiply it. So really the only problem that we have... Oh, and I should... CPU16? Yeah. The only problem that I have is figuring out how to map a position, like this element P, into the lookup table in the first place. And so there's a couple different ways we can do this. And it's kind of tricky, right? It's a kind of touchy problem. I'm going to do a very straightforward version of it first, but we will probably have to do something fancier in the future, and I can try to explain why. So let me show you what's going on here. So a voxel, you generally think of as something that, you know, looks like this or whatever, right? It's a bunch of cubes in space, and we just think of looking up into them to find out what's inside a particular region of space. But it's worth noting that you don't have to do that for your voxel, right? If you think about how we view the world in a 3D game, it's a perspective projection. So there's a near clip plane and a far clip plane. And if you imagine putting one of these voxels in world space, right, like this is here, it would be something that looked, you know, like this, right? And what you can see is that the space of things that's covered by the camera view is a different sort of geometric density in screen space as this voxel would be. Because when you get closer to the viewer, the cells are much larger per unit of screen space than when you get further from the viewer when they're much smaller, right? So chances are, indexing into the voxel, we don't really want to do world space, because look what happens if we try to align our voxel so that it covers the entire camera space. Well, it's got to be as big as the far clip plane, right? So we know that it has to look basically like this. Right? That's what we know. However, you can see that now a bunch of our voxel is getting used for stuff that is not on the screen. And so probably what we would want to do to make more economical use of it is to bend the voxel so that it actually looks more like this. Right? Now you may think that there is some kind of that's like really difficult to do or something. It's like, oh wait, but we only have a 3D texture lookup and we just have UV coordinates. Remember, we are allowed to pass anything we want to the lookup, to the 3D texture. we're under no obligation to pass world space coordinates. So what we could do is we could use a perspective divide to actually prospectively project our UVW coordinates so that they create a warped lookup. Now, the voxel doesn't warp. It's still just space and memory, right? It's not changing what we're storing. It just changes how we look up into what we're storing. And like I said, that's probably something we're going to want to do. We just don't want to do it right away because it just adds another thing to get wrong into the set of things we're trying to do right now. And so getting things working one at a time is a lot better. So what we'd rather do is get the voxel working first regularly because that's much simpler, and then work on warping it after, right? Okay. So the next thing we need to do then is come up with some simpler scheme for indexing into our voxel, and there's a pretty easy way we can do that, especially since we're computing this offline. We don't have to care about the speed at the moment. We can do something pretty basic. What I'm going to do is I'm going to take a min corner and a max corner. I'm just going to spin through all of the lighting elements that we computed, and I'm just going to compute the bounds, right? I'm just going to say, all right, I think we've got a real 32 minimum and real 32 maximum here. Do I have these? I don't even know. Yeah, okay, there we go. So all I'm going to do is I'm just going to set these to the min and max values they can possibly be. Now you'll notice I set the min corner to the maximum and the max corner to the minimum, right? Which is like an inverted infinity rectangle, which by the way would be a great name for an album. What I want to do is I want to go through each of the lighting elements that we have first, and I just want to take in the position and set each of the min corner and max corners to the lowest possible x, y, and z value and the highest possible x, y, and z value we ever see, right? Now, I don't know if we have a math function for this. Oh, hey, look. We actually have this function already. Too bad we only have it in 2D, huh? Because that's actually what we want. Oh well. But that's okay. No big deal. So all I want to do here is I want to say, all right, the min corner for our vector you can see here I've got an E value here for each of these guys. I don't know why. I guess this is old code, so it still uses the real 32 value. Oops. There we go. So what I want to do is I want to go through each of the min corner, max corners. And I want to set them to the minimum value and the maximum value of themselves. Like so. And whatever the new value is for P. There we go. So basically just spinning through here. Oops, I think I could call it minimum. So basically what this will give us is this will give us the minimum possible value that anything can take and the maximum possible value that anything could take in our system. Now, once we have that, we then know the bounds of the voxel in 3 dimensions. So at that point, we can actually map things into the voxel in a fairly straightforward fashion just by using basic discrete math, right? So let's say we've got this min corner and this max corner, the min corner, max corner. I want to expand them a little bit just to give us so that we're not fetching to the very end of them. I find that usually that's a little bit more convenient. You don't have to do that if you don't want to. If you want to ride the epsilon edge, you can definitely have, you know, you can be as brash as you wish. There we go. So I'm just going to expand it by pushing the min corner and the max corners out just a little bit. And then what I'm going to do is I'm going to create the span value for these. And what the span value is I'm basically saying, all right, I've got the min corner, the max corner. I know what I'm going to have to do is every time a position comes in, I need a way of mapping this into my voxel. We've done this a lot of times before, like when we want to put things into grids, right? And so you imagine we've got sort of a thing that looks like this, and so on. For each one of these axes, we're going to want to say, oh, we've got a p-value that came in here. Well, that better not be, because that's outside the zone. Let's say p-value that came in here. We just need to figure out what grid square it's in. So all we're going to do here is we're just going to figure out by dividing by this, you know, cell size here, essentially, how big the cell size is. We're going to figure out how many of them we would have to go to get to this one. And we're going to truncate that value, obviously, because we want it to be stored. We want to produce the next lowest value, right? So if it's here, we want to produce 0, not 1. If it's here, we want to produce 1, not 2, right? So we want to create basically the divide truncated down. And that's all we're trying to do. And like I said, we've done this before. We did this in the world code. Let's see where we've got that, just so I can show you what we're talking about here. This I think we did. Oh no, we switched it to a hash table. Never mind. Never mind. We didn't do that. I think we did it at one point. We just don't do it now. So anyway, that's all I really want to do. So what I need to do is create that span value, and the span value is just going to be the min corner minus the max corner. So that now we have an x, y, and a z value that is how big each of those dimensions are, right? In fact, I could just call this dimension. So then what I need to do is come up with a way of doing that divide. So we know that we've got these various cell values here, and we know how big they have to be. So what I'm going to do is I'll maybe compute that like light lookup x or something, y and z. And I'm putting these in an arbitrary order here. It doesn't really matter which order we do them in. If we wanted to be fancier, maybe we would put them in reverse order because that's a little more consistent with how we tend to do things. We tend to put the x as the minor, the y as the major, so the z would therefore be the, you know, the most major at that point. So maybe that's the easiest way to keep that. Doesn't really matter. The choice is arbitrary, how we wish to look up into our texture. All that matters is the one that we want to look up in Z can be smaller. Don't ask me why I made that. 256. We probably still could. I don't know. How big would that be? And that's a lot bigger, though. 64 megs just for the lookup if Z is not undersampled. All right. So anyway... back there. So anyway, once we know what those are, we can then produce the size of a cell because we now know that like the cell dimension is just going to be a series of divides, right? So we've got the dimension x, and we need to divide by how many of them there are in x, right? We've got the dimension y, and we need to know how many there are in y. So we can now produce how big each cell is. And furthermore, we can produce the inverse of that as well, right? So if we wanted to do the inverse cell dim, which is what we actually need, in fact, I don't know that we ever need this one. So we could just, I think we might be able to just produce the inverse cell dimension always. which is just 1 over how big the cell is. And so what that will do, right, is the inverse cell dim is something that takes an actual position and turns it into an index into our voxel, which is exactly what we want. So we know that the voxel position is the element position times that inverse cell, right? Now we have to be careful here because really that just gives us the span, the stepping. We still need one more thing here, which is a way of centering it around where the voxel is. And again, that's the min corner part of that, right? So by first subtracting away the min corner, now we know we're relative to the inside of the voxel space. Then by Hadamard producting it with the inverse cell dimension, we then know, okay, we are now in the numerical space of this voxel 0, 1, 2, 3, 4 in each of the dimensions. At that point. But we still have fractional here, and we don't want to look up by fractional. So we need to truncate each of these to get the actual voxel x, y, and z. So to produce those values, we want to do a truncate and to just truncate each of these to place it into the voxel at the location it should go, right? And I guess I said we were doing it this way, right? There we go. And that should basically do it. Oh, this is off of the destination there. That should basically do it. Like that pretty much, you know, modulo bugs will give us the complete set of textures we would need to pass down to the card in order to determine all of the lighting gathers that we might need to do, right? And that's it. That's all there is to it. So at that point, we would just need a way of sending these down to the card, and then we could actually use them when we are actually doing our lighting equations. However, we, obviously have a bunch of work we would have to do there, and I don't know how much time we really have here. We only have about 15 minutes left. So I'm not really sure. I guess what I'll do here is say, well, you know, inside Handmade world mode here, when we output this lighting, maybe I'll just say, hey, like, I guess what we'll say is, all right, let's have a lighting texture in there. When you generate the lighting, why don't you also generate the lighting textures, just so we can test it, right? And that should run that code path. We just can't see if it's actually working. We don't know what it created, and so, you know, there's that. I guess what I could do real quick, and this does seem like maybe a good idea, is I could make an output routine that just puts little splats quads everywhere to show the values of the voxel in all locations. That actually seems like a pretty good idea. Yeah, let's do that. So let's figure out a way to make that happen. when we call output lighting here, let's actually call output lighting with the test textures as well. And so here where we're going to do I don't know why I called it dest. Here where we're going to output this stuff, let's say that if we got the textures, that we're going to do some kind of a quad output lighting that comes just from those, right? So what I'll do here is I'll copy this routine and I'll just call this some kind of debug texture output, right? And we don't really know ahead of time how many there are because we don't know how many are in these textures here. So we'll probably have to pass the lighting solution, I guess, just so we have that value. We could store it in the textures as well, but again, this is just for debug, so it probably shouldn't matter. And so then what we could do here is we could just say, well, all right, let's just step through each of these axes. And let's just output the constant of the voxel. Because that way at least we know what's in there, right? And that's better than, you know, starting next week not knowing whether we built our voxel correctly and we still have to, you know, figure out if what we sent down to the card was even remotely correct. All right. So the textures lookup, we are going to get the first one out here. So this is our like first index. Or I guess we should just say it's just our index. And we just want to loop. So we're going to grab out the pnext. I guess I don't really need to do it. Well, I'll do it though. So we're going to grab out that pnext value. We're going to look at it, but then immediately after we'll just keep going on it. Like so. So we know that this is the location, and we know the color is just whatever that index is. So that gives us the position and the color value. And so now we can make something, we could, you know, push a cube or something on here, I guess that had that lighting color. In fact, maybe that's what we'll do. Since we don't have normals anymore, right, at this point, maybe that's exactly what we'll do. Let me see what our options are for doing something like push cube. So push cube would take the render group, the bitmap ID, which is just the white bitmap. We don't want an actual bitmap on there. We know the position. We know the radius should just be some small radius. And yeah, I don't know what to do about the height exactly. And then the color is just going to have to be an unpack. It seems dumb to pack and then unpack this. in that way, but what are you going to do? This code really needs to be cleaned up a bit. In fact, the way that we're doing this now, in fact, I could clean this up right now. Let's just do this. It looks like the push cube. What is the difference between these two routines? That one takes a bitmap ID. And this one takes the resolved bitmap. And it also takes an emission value. All right. So let's just make this take a color value. And I guess the only question is, can we trust that the people who have passed this in are going to actually pre-multiply it properly? All right, maybe I won't do that. Maybe I won't do that. All right, so what we need to do here is we need to unpack this, this normal value. See here. So this unpack is going to leave things essentially the way they are. So when we do that unpack 4x8, these are going to be in the 255 space. So we really need to do, you know, this to get it out of there. So once we've got that, we can pass it down. And I guess that's fine. All right. So let's see here. This should allow us, if we do this output texture debug bit here, this should allow us to see cubes that represent everywhere that we stored a lighting sample in our voxel. Now, it doesn't quite show us yet exactly whether the voxel got sorted properly. It would just show us whether we stored stuff properly at all. The reason I say it doesn't say whether we sorted the voxel properly is, well, we're going to get stuff out, and we're going to draw it at the location that it's supposed to be drawn at. So even if we stored it in the wrong voxel location, we would still output it in the right place. So at the moment, we're really only going to be able to debug. Well, of course, since we don't see anything, that's a good sign that we still have bugs to work on. We're only really going to be able to debug the fact that the things were stored, and we'll have to come up with a cleverer way to figure out whether they were stored in the right place, right? So we have those two separate things to do. All right, so let's start by stepping through this. I'm gonna switch out of optimized mode. And I'm gonna go ahead and set a breakpoint. I think it's called lighting test. Well, let's just go output lighting textures. We don't really care about the rest of it, I suppose. So we don't care about lighting test actually, because that's mostly irrelevant. We got to wait for a while for our extremely slow debug to happen. And then we gotta take a look at this. Although now I think about it, the other thing I probably should do is just turn the ray casting count down, because we don't really need to be doing anything particular with the lighting solution at this point. So we're really just blowing a bunch of random time on that. In fact, let me go ahead and do that. Oh, it is only doing 8. Man, the debug version of this is so much slower. I wonder why. It would be interesting to see what... I guess probably because all these things turn into function calls. Well, alright, we'll wait for it. This is one of those things where you really wish you could just put a little block around something and say, optimize just this one routine. But Visual Studio can't really do that because it won't inline functions who are outside of that block. Like it's kind of a mess. All right, so if we take a look at what happens here, let's first start by trying to look and see whether the min corner and max corner are reasonable. Those do seem pretty reasonable. I guess it makes sense that they're basically exactly the same values because of the way we sort of symmetrically create the world. It is a little suspicious, but I'll give him that. So let's see here. So if we compute one of these voxel p-values, see what the x, y, and z is. 144, 130, 10. Those are sane. We look up the lookup at, which should always be 0 first time through. We do some color packing there. We say OK. The lookup value is going to point to us. We are going to point to nothing. We set the position just fine. That's all good. And then we've got our destination color that we set. So that all seems pretty reasonable. So let's take a look at output texture debug. So we never get in here, even though we saw that. Oh, wow, not a great day for, oh man. All right. Well, I'm glad I didn't spend too much time looking for that. It's like I didn't even pass the values that we were trying to look up. That's great. Good job. Nice. Wonderful. Wow. Anyway, let's go ahead and see how that goes here in release mode. All right. So that did produce a bunch of cubes, but they are weirdly positioned. And if I switch to the non-debug camera, I can't see them anymore. So something is a little off. I'm just not sure what. We are still storing the element P. When we do the output texture debug, I'm not sure what's going on there. They seem to be slightly invalid values somehow. I'm just not sure how. Here's a question. Can we do... Is it that? That did work or that didn't work? That looks like that works surprisingly well. Should do that more often. That seems like a perfectly sane value. That does not look anything like a perfectly sane value. So how is that... How is that getting generated? So the alpha should always just be 1, right? Does RGB A unpack already do that for me? I mean, it sure doesn't look like it, right? That should produce the 0 to 255 version of the unpacked values. So I'm not sure what's up with that. Let me try this. So that looks like we are storing lighting samples pretty much the way they should be stored. We don't know if they're in the right Vox containers. So it looks like it's just the color that is wrong to me. So all we have to do is just debug the color value, and then we should be good to go. It looks like the front emit RG and B, they're being clamped 0 to 1. Then we're doing an RGB pack 4x8. It looks like we forgot the 255 there. Yeah. So basically this is the only problem. And then I think we're good. There we go. So I think we now have a nice little world of lighting samples. There we go. And we're pretty much ready for next time. So let me go to the Q&A, and I'll remove the pragma. Anyone have questions on what we did? I'm pretty interested to see how this works. Like, I'll be very interested to see how the if gathering works well. Because at this point, the other really interesting thing that I find about this is we no longer really have to care where we put the lighting samples because if we reconstruct the lighting samples per pixel, then we can scatter our lighting samples around the world in whatever places make the most sense for creating good lighting solutions. We don't have to put them in particular locations because we know we need to output the values at that location directly. Ah, thanks. Okay, so you guys made a gist that was... This is a pretty advanced... Wow, you guys got a lot of stuff in here. I don't see any questions. Let's see. Room 0001011. Maybe it's a non-issue, but because the entity is tilted when it walks in front of a cube, it is being cut. Is there an elegant solution for it? Well, actually, we kind of have some solutions for that already. I don't know if we want to play with this too much at the moment, but basically what we see here is a little bit difficult because we don't have actual representative artwork in right now. So the artwork is kind of drawn at an angle that is not the angle that the actual artwork is for the game. So the cutting problem will actually be lessened a little bit, but we already do have some solutions in there for that. We have a bias value that you can add in, which causes things to appear in front of where they actually are to prevent these kinds of problems. So, for example, yeah, like if I put the hero bitmap back in so that we have somebody we can actually drive around. So there's the clipping. Well, okay, we've also have that giant light in the way, which isn't going to help. But you can still see the clipping. There we go. You can see the clipping problem that you're talking about there. So we have ways in which that can be modified. So for example, if we wanted to, we could increase the degree to which bitmaps get biased z-values. For example, let's say, let me see where we've got this here. This is the lighting code. We don't want line segments. We just want bitmaps. So you can see the z-bias value here that gets added into the sprites that we output. We have really, we can adjust this however we want. And again, it's always kind of a hack to try and put things that are 2D into 3D. So there isn't really a right answer to this, but you could imagine making it a much more pronounced z-bias value, right? So for example, and this is, of course creates a problem with the near clip plane, but you can see now there's actually that hero appears in front of these cubes up until it gets clipped by the near clip plane, which is actually out pretty, if I pull back a little bit here, now you can kind of see that he doesn't get clipped anymore, right? So we do have, sorry about the light that's in the way there. We were, like I said, we're playing with lighting, so we're not really in a position to start talking about sprites. So you can kind of see how the z-bias value does allow you to deal with these problems in some ways, but it's always a little bit of a trade-off because, you know, the more z-bias you add in there, the more you get problems of like, I don't know if I can go downstairs anymore because we kind of caved ourselves off, but you can imagine problems of like now when I'm standing in front of, you know, this red piece right here, for example, maybe I can get in a place where I should be clipped by it, like right there, and I'm not. So the problem with using z-bias too aggressively is that you can only really put it to a certain level before it becomes a problem, right? I'm not sure what the really best way to deal with some of this stuff is in the end. We just have tools we can use to try to combat the obvious problems. My hunch is we won't have to do as much with it in the future because the artwork will be centered more properly on the squares, and we won't have as much problem with overlap, but it's hard to say, right? So we'll play around with it, and you know, we'll see how bad it is when we actually have to put together the final stuff. But there's never going to be, I don't think, a perfect solution when you're trying to place 2D things in 3D. When we made the high and low priority thread queues, how did we make the high queue actually have a higher priority? I can't find the difference between them in the implementation, if that makes sense. That nomenclature is about how we are treating the queues in our code. They are not higher or lower priority in Windows. So what the high priority queue is it's a thing that all threads will take work out of. So here, I can sort of show you. Okay. So here's where we create the queues, right? And we create 2 low priority queues and 6 high priority queues. The high priority queues are strictly for doing CPU work that has to be finished immediately, right? So it's stuff like the software renderer runs through the high priority queues. The low priority queues are things that are just waiting for stuff to happen. Like, oh, I have to do a load. Like I have to load a file. And so I'm waiting to like load some data out of the file or something like that, right? So if you look at how those end up getting used, what you can see is that here we add entries, for example, to these low priority queues, right? And then those low priority queues are going to call us back, for example, on this, I believe, no, it's not quite here. Where is it? Where is load asset work? There it is. So the low priority queue is going to be calling back here at the load asset work call. Right? That's what's going to happen. So if you take a look at how that sort of thing works, and you take a look at instead how, say, the renderer works, there's a big difference between the two of them. And the big difference is the complete all work operation, right? So when we use the high priority queues, what we tend to do here is we push a bunch of stuff into these queues, and then we say complete all work on the queue that we used, right? Whereas when we're doing something that's just a slow overlapped operation, we push stuff onto the queues, but we never call complete all work, right? Now, why does this make one a high priority queue and one a low priority queue? Well, the reason is because when we call complete all work, over here. When we call complete all work, what we're essentially doing is taking a queue and we're forcing ourselves to do all the work out of the queue that we can do, right? So we're just like going down the... we're pushing a bunch of work into a queue, then we're forcing ourselves to, even on the thread that launched that work, we're going to sit there and keep doing work until the queue is empty, right? Similarly, if you take a look at how the thread proc works, it's just going to do get work out of the queue, do the work that we pull out of the queue, and then wait if there isn't any work to do, right? If we run out of work, we will just sort of pause, right? You can see like we should sleep. That value is false. If we did work, if we didn't find anything in the queue, then we say that we should sleep, right? So essentially what we did is we just partitioned our work into 2 queues. One that will just, we push everything into, we know that the other threads as they wake up will do work out of that queue. And then we will also sit there on that queue and just do the work that's in it till we're done. So everyone will focus on that queue work, and it will happen, right? The low priority queues are different. There's just 2 threads sitting around doing work in those queues all the time, if there's anything in them, but nobody will actually block on them to finish, right? So we don't actually do anything to try and make these queues higher or lower priority in any particular sense. All we're really doing is all we're really doing is treating one differently than the other, and we put more threads on one than the other, is another way that it's higher priority, right? If we wanted to be fancier, we could be fancier. What we could do is we could say, all right, all threads when they wake up pull out of the high priority queue first, and if there's nothing there, then they pull out of the low priority queue, right? So we could have actually made all threads that exist focus on the high priority queue work. But the reason we didn't do that is because we're not really treating the low priority queue as something where work gets done. It's more something that just sits around waiting for files to come in, right? So there didn't seem to be a need to like actually try to make ourselves be perfectly subscribed. Hopefully that makes some sense. If I was to guess, I would say the problem is not the 2D entities in 3D space, but rather 2D entities with 3D entities. If those cubes were sprites like the trees, it would work just fine. Sadly, that's not really true. I mean, I guess it depends on how you look at it in terms of your how you want to phrase it. So maybe this is what you mean. But the problem is, in fact, the 3D-ness of the world. So if you look at the fact that these want to be in perspective, and you can even see how the trees are warped in perspective slightly as well, the fact that we want some perspective to the world, that's actually the problem. It doesn't matter whether they're sprites or cubes or anything else. As long as there is a flat surface that wants to have some perspective to it that can flip, that's the problem. If we let this sprite fold back to match what was happening here, then we'd have no problem, right? But what we're trying to do is fake it so that the world has the ability to have perspective in it. And because we're doing that, we run into these problems, right? So if you want to call that 2D entities with 3D entities problem, that's fine. It's really more a 2D entities with perspective problem. Might be the best way to put it. In the software renderer, we aligned the memory to 16 bytes for SIMD, but then we used the unaligned load and stored instructions. Why is that? So it depends on the situation. One thing that was very strange, I guess I don't think it's actually that strange. My recollection was that we found that it was no slower to do unaligned writes than aligned writes. That was my recollection. However, we don't use all unaligned reads and writes. For example, this is aligned, right? That's an aligned load. These are both aligned. That's aligned. So all of our pixel loads are actually aligned. What's unaligned is reading from the texture, if I remember correctly. Actually, I guess the text, but the texture, I guess, isn't loaded. Well, all right. So I don't know. Do we still have any unaligned loads? Where are the? I don't see any unaligned loads. Where are the unaligned loads? Are they gone? I guess they're gone. I remember using one as well, but I guess it's not there anymore. So, Alex Kelbo, what unaligned load and store, I guess, are you talking about? Am I searching for the wrong thing? Pretty sure load you and store you is the mnemonic for them. Yeah, I don't remember that actually being a speed win, though. I think we just... I can't remember if it actually helped. I think that modern chips may just not care very much about unaligned versus aligned. So I don't know if the chip actually cares. But we did do it. And that said, this is actually a pretty old chip. So if chips didn't care, this chip might still care. And the other thing is to remember is the reason to align those is actually not just because you want to use aligned load and stores. It's also because you don't want false sharing of the cache line. So you need to make sure that the tiles of the tiled renderer end on a cache boundary. So, right, if you want to have thread 0 working on this tile and thread 1 working on this tile, right at the boundary here, you have to remember that if both people are writing to pixels that are at the boundary, you have to make sure that they're not sharing a cache line. Okay? Because what'll happen is if thread 0 and thread 1 are both pounding on the same cache line, you're going to be in a world of hurt. So you want to make sure that the cache lines, which are 64 bytes, you want to make sure that they end right at the end. And this one starts on a fresh cache line. So that the cache line doesn't have to bounce back and forth between the two threads to write to the different portions of it. Right? So the real reason to be aligned there, I suspect, is actually much more stringent than the unaligned loads and stores would be. It's actually because you would get bad memory behavior at the boundary due to false sharing as the cache line bounced back and forth between the cores. So anyway, all right, that's about it for today. I think we've covered enough. I'm going to go ahead and close down the stream. All right, everyone. Thanks for joining me for the episode of Handmade Hero. It's been a pleasure coding with you, as always. If you would like to follow along with the series at home, you can always pre-order the game on handmadehero.org. It comes with the source code, so you can follow along at home. We also have a forum site you can go to if you want to ask questions, a Patreon page you can go to if you want to support the video series. That is, if we don't get deplatformed for, I don't know, doing something Patreon doesn't like. Apparently, it's on the table now. We also have a schedule bot that tweets the schedule at you if you want to go ahead and know when we're going to be live, and an episode guide that you can go to if you want to catch up on old episodes. For example, if you want to know about aligned loads and stores and when we put those in and out, you can go ahead and use that. It's got a handy search feature too now. That's pretty awesome. That's about it. I will be back next weekend to play around with getting the GPU to reconstruct that lighting that we send down to it. And then we're getting close to having some real lighting. We're going to have to start figuring out how we can put the lighting computation on the graphics card. That's going to be a little bit of a journey. But hey, you know, what can you do? So we've got a couple more weeks of lighting left, and it's starting to come together, which is kind of exciting. So hopefully you're joining me for that. Until then, have fun programming, and I'll see you all on the internet. Take it easy, everybody.